Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math is, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into section 2.6 of the Big Ideas Math Integrated Math 1 textbook on solving absolute value inequalities. This is the final section in this chapter on solving linear inequalities as a whole. 2.4, I think, was really the bread and butter of, or meat and potatoes, whatever you want to say, of how you solve inequalities, and I think that's the pinnacle of what we do. 2.5 is solving compound inequalities. Not all of them are like that, but you use a lot of 2.4 for it, and we use 2.5 to do a lot of 2.6 solving absolute value inequalities. At the end of my 2.5 video, I did stress that what you do here was important for what is about to happen now. So I am going to state right now that we will, for absolute value inequalities, a lot of them will be compound based. I think that's pretty much the requirement for these ones here. So if you didn't watch that video, or if you don't know how to do compound inequalities, I have the right to go faster on that portion of the problems once we're set with that. If you remember how absolute values for equations worked, this will be kind of the same. If the absolute value of something equals this, either it equals positive this or negative this, now the absolute value will be greater than or less than something, or however you want to put it, and now it'll be greater than or less than some values, and we get to run into those. So there's that portion of it. We have 40 problems in total to do before we hit our review and chapter test and cumulative assessment at the end of this chapter. So if you want to follow along with this, jump to the description section down below. You can download this PDF and perhaps print it out, do whatever you want with it. I'm going to start with the lecture and go to the problem set. If you're here for the problem set, jump to the description section down below, find the timestamps for individual problems that you're looking for, and the playlist is down below if you want to find section 2.5. Without further ado, I'm going to go ahead and get started. We are going to solve absolute value inequalities. Like I stated, instead of equations, it's going to have the absolute value, but maybe greater than or equal to something or something like that to solve. And then we use absolute value inequalities to solve real life problems, word problem scenario. So our new phrase, absolute value inequality, and I haven't heard of this before, absolute deviation. It sounds like how far away you can go from something at most, because I'm thinking deviation, deviate off course, how far you can run within 3 feet of the base runner's line down the first base line in baseball. Your absolute deviation is 3 feet. Maybe that's what they mean. Anyway, here we go. An absolute value inequality is an inequality that contains an absolute value expression. Boom. For example, right here and right here, these are absolute value inequalities. Recall that absolute value of x equals 2 means the distance between x and 0 is 2, right? It doesn't just mean make it positive. The idea is stating that you would go 2 units either to the left or right from 0. Now, these ones mean something a little different to us because it's not equals, but it's less than or greater than. The inequality absolute value of x is less than 2 means the distance between x and 0 is less than 2. You now have to be within 2 units of 0 in either direction. You either have to be within 2 units this way or within 2 units that way. If you're at -1, you're good. If you're at 1/2, you're good. If you're at 3, no. -10, no. It's not just being less than 2, it's being within 2 units of 0. Now, there are ways that we write what that is specifically. If you're within 2 units of 0, you're either greater than -2 and, well, sorry, not either. You are greater than -2 and yet less than 2. You know, we would generally write this as a compound inequality like this, but now the actual phrasing of that, you can do that. But the actual phrasing is x is now greater than, less than 2, x is less than 2, and x is greater than -2, like that. I guess they wrote that right here, but the opposite order. Now, the absolute value of x is greater than 2 means the distance between x and 0 is greater than 2. That means you have to be more than 2 units away from 0 in either direction, positive or negative. So, greater than 2 units this way, greater than 2 units that way in either direction. You can be -4 or +4. You can't be 1. You know, things like that. So it's a split. It's this or that on one side or the other. So if absolute value of x is greater than 2, x is either greater than 2 or x is less than -2. And I guess they wrote that here as well. I'm kind of picking up on a pattern for these two things, though, right here. They're showing the -1 first and then the +1 second. I'm not a big fan of that for a lot of reasons. We didn't do it for equations. I want us to remember how this thing works and operates. I want the first one to look like the first one here, but dropping the absolute value, and you'll see that I do that. You switch the sign in the inequality on the second one. There are a lot of reasons why I'm going to write it this way and not the way that they did it there. So if they're going to keep doing that, I just want you to know I'm going to do that. All right, you can solve these types of inequalities by solving a compound inequality. That's why I stated it's good to know these. So I'm going to speed on through these parts once we set them up and just make sure to just solve them. So to solve this one is less than c for values greater than 0, you have this split of these two things. Again, I'd rather write this one first, this one second. So what are they saying? If the absolute value of something is less than a positive number, you can either be less than the positive version of it. Sorry, I shouldn't say either. You have to be less than the positive version of it and yet greater than the negative. Because again, greater than the negative means to the right of the negative values. Less than the positive is to the left of these. You're within this many units of 0. You're between them. Absolute value is greater than it. Now you got to be outside of them. So either greater than the positive or less than the negative. Remember, less than the negative is to the left of the negative, outside of them, like that. So make sure the absolute values by itself, set it up, and solve them when you do it. And of course, you can replace these with these equal to's or equal to's. Okay, solve each inequality, graph each solution if possible. Absolute value of x plus 7 is less than or equal to 2. Just like absolute value equations, we're not trying to solve for x immediately. We're trying to make sure that we understand what x plus 7 can represent. The absolute value of something can be less than or equal to 2. So either that something can be, I'm going to write this, less than or equal to 2, and it needs to be greater than or equal to negative 2. We'll subtract 7 from both sides to get the result. X is greater than or equal to negative 9 and less than or equal to negative 5. I get why they're doing it right here, so their compound inequality works better. So there's their solution once they subtract 7 from both sides, and they're the set of x's that make this true. Not x plus 7, but x, right? X plus 7 has to be within 2 units of 0, but x needs to be within 2 units, I guess, of negative 7 in this direction here. Okay. Oh, there was a second example. Did they show it? Oh, okay. This one, this one's good to talk about. This is kind of a special case. The second case says absolute value of 8x minus 11 has to be less than 0. Well, think about what it's saying. I take the absolute value of something and it has to be negative. We can't do that. We can't take the absolute value of something and make it negative. Remember, that's what less than 0 means in this case. So they say it. By definition, the absolute value of an expression must be greater than or equal to 0. The expression here cannot be less than 0. The inequality is no solution. There's no value of x that will ever make this true. There's no number I can take the absolute value that will be less than 0. So that doesn't work. Interesting that they don't have it as its own special case. So we might see these in the core set of problems. So get ready for that. That's cool. I like it. Okay. Example 2, solving absolute value inequalities where we are greater than or equal to or greater than So this one's isolated, so we will set this in and of itself. The absolute value of this must be greater than 5 units, greater than or equal to 5 units. So we must be greater than 5 units of 0 in either direction, greater than 5 or less than negative 5 or equal to. Greater than or equal to 5 or less than or equal to negative 5 is our setup. We solve these individually, add 1 to both sides, add 1 to both sides here, and there's our setup. It's not a compound as a single inequality. It's either this or this, and there's our split of our graph. Again, I'm not going to spend time on the 2, 5 stuff that we already did, but these are our 2 values for C outside of that set. Part B says absolute value of 10 minus m is greater than or equal to negative 2. Now, here's the interesting part, right? Because, again, negatives, we're used to when it says equal to, we say, oh, there's no solution, can't take the absolute value of a negative. But this says greater than or equal to negative. You know what some other numbers are that are greater than or equal to negative? 0, 1, 2, 3, 4, 5, 6, positive numbers, and 0, which are things you can take absolute values of. What's a number that I can plug in for m that doesn't make this work, that doesn't stay greater than a negative number? Absolute value of anything will be 0 or positive, so anything will work here. So what do they say? By definition, it must be greater than or equal to 0. So absolute value of 10 minus m will always be greater than negative 2. This is all real numbers. All real numbers are solutions. That's the answer. You can plug in anything so long as it's 0 or positive. And anything here greater than or equal to negative 2 will be 0 or positive, even if it said greater than. If it said less than, no, you can't do that. That's not going to work. If it said equal to, no, it's just not going to work. Part C. We have to isolate the absolute value before we solve. So check this. They are going to first subtract 1 from both sides and then divide both sides by 4. Now it's by itself, and now we do our setup. We do the split condition of either greater than 5 or less than negative 5, and we solve by adding 5 to both sides, dividing both sides by 2, and now we have the set less than 0 or greater than 5. If you remember out of section 2.5, we actually had all OR cases have different expressions on both sides. There was an OR, but it wasn't, if this was 2x minus 5, this would probably say like x plus 3. they would be different. Now they're going to be the same. So you get to do the same thing on both of them, and doesn't mean you get the same answer, like plus or minus this number, but you get to do the same action. Plus 5, divide by 2, and then you solve and you graph. So that's the instances of those when you get the split. Again, when absolute value is less than, you stay within that distance. That's an AND case. When it's a greater, absolute value is greater than, we have to split outside of the positive and negatives of those cases. Real life problems. Let's solve real life problems. I have real life problems. The absolute deviation, here's where they define it, of a number x from a given value is the absolute value of the difference of x and the given value. I don't know if I understood that. Absolute deviation equals absolute value of x minus given value. Okay, we'll figure out what that means in a second. Let's use the example. We'll understand it through that in a moment. You are buying a new computer. The table shows the prices of computers in a store advertisement. You're willing to pay the mean price with an absolute deviation, there it is, of at most $100. So the average price of these, okay, that's an interesting way. I should go about life this way. This will solve one of my real life problems financially. We'll take the average of these, and we're willing to go within $100 in either direction of that. We don't want to spend too little, because otherwise these seem like cheap computers, I guess. We definitely don't want to spend too much because it's just out of our wanted budget. How many of the computer prices meet your condition? So, in understanding this, we have to take the average of these numbers. So where do they do that? Right here. They just said you add them all up, they become this. There are 10 of them. The average is $664. Now, they are not going to just write minus 100 plus 100 literally, but what they're going to do is set it up as an inequality. Our difference between, the distance between the difference in these numbers, okay, now I understand it. The difference between these distance of our numbers and the average must be within $100. Within $100 of either direction, plus or minus. So when we add 664 to both sides of this thing, which is the same thing as saying 664 plus 100 and minus 100, you get between $564 and $764. So the only computers I'm going to be able to want to purchase are the ones that are within that range. So not this, yes, this, not this, 764, yes, this, not this, 564, yes, no. I think these 6 qualify. 1, 2, 3, 4, 5, 6 qualify right there. There's our absolute deviation. Okay, so I'm getting it. We'll probably have to write our own absolute value inequalities, like we had to do a bunch of absolute value equations as well. Probably not even in word problems. So as a concept summary, just as a whole, if there's not, I don't know if there's more to this afterward. One step in multi-step inequalities, you follow the steps, reverse the inequality symbol when multiplying or dividing by a negative number. Oh, this is just inequalities. We're good. Let's look at absolute value. If necessary, isolate the absolute value. Yep, get it by itself. Then write it as a compound inequality. Okay, they don't say much more than we would do. Okay, guys, I'm just going to jump to the vocabulary and core concept check. Sorry, again, I sight read these things. I don't see them beforehand, so just doing it with you, learning it at the same time. Number 1, reasoning. Can you determine the solution of absolute value of 4x minus 2 is greater than or equal to negative 6 without solving? Explain. Yes, I can. You can take, anytime you take the absolute value of something, the result is 0 or positive. 0 or positive is anything that's greater than or equal to negative 6. I should say greater than negative 6. So therefore, this is all real numbers. X can represent any real number. Because the absolute value of anything will always be 0 or positive, any number greater than negative 6 let's see. Any number greater than 6 will be a solution. Let's see. Every solution, whoopsie, sorry about that. Every solution will be greater than negative 6. Or equal to, but not equal to, right? Therefore, all real numbers is the solution set. So nothing to calculate. I don't even know what you would be able to calculate. It's just not a situation that allows us to do actual calculations. So they say without solving, yeah, that's how we solve that. Number 2, writing, describe how solving absolute value of w minus 9 is less than or equal to 2 is different from solving absolute value of w minus 9 is greater than or equal to 2. The idea is the split condition of what you're doing. The less than or equal to, the less than, I have a thingy, give me a second. The less than or equal to 2 situation means our expression, our absolute value expression, no, our expression needs to be within 2 units of 0. Now this includes 2 and negative 2. Including 2 and negative 2. And this is going to be the case for the next one as well. And whereas the greater than 2 situation means our expression must be outside of 2 units of 0, including 2 and negative 2. So that means that we can be 2 or negative 2 in either case, but we do a split condition of that one way or the other there. And we're going to be taking a look at quite a bit of those in just a moment, kind of formatting this. This is really tough for me to write these ones because everything else is in the way. But without further ado, we're going to go ahead and get started on the core problem set, numbers 3 through 40. Again, I'm going to be speeding through the compound inequality portion once we get that set up, but of course they'll probably throw a lot of word problem stuff, getting us a great mix and deal of problems that we have. So we begin with numbers 3 through 18, where we solve the inequality, graph the solution if possible. So on number 3, we have absolute value of x is less than 3. We must stay within 3 units of 0 to the right and within 3 units of 0 to the left. That's greater than negative 3. That's an answer. I'd rather write it like this personally. X has to be between negative 3 and 3 as a graph. That'll clearly show with 0 as well. And by the way, in my lecture portion, I never spoke on double checking with 0. We'll see how much it'll make sense to be able to do so in these situations. For this one, it's kind of basic. Yeah, absolute value of 0 is less than 3, but we'll try it with kind of bigger numbers as we progress along. Number 4, absolute value of y is greater than or equal to 4.5. This is where we must be outside of 4.5 units in either direction. So either greater than or equal to 4.5 or less than or equal to negative 4.5. And there's nothing else I can do on the split. That's the answer. But when it comes to graphing this thing, again, it is a split. We have to be 4.5 units away in either direction. And the thing about these that I want to stress, and I'll be saying this more as we go along, is that, there are only 2 directions on a number line like this. I mean, this can be in a real world scenario, right? In multiple directions, left, right, forward, back, up, down, things like that. If you're saying something like, at SeaWorld, you have to be outside of, if you're within the first 3 rows of, the dolphin tank, whatever, you're in the splash zone. So people read that as, oh, it doesn't matter where I am around the pool, around the tank. If I'm within 3 rows, I'm in the splash zone. Adults are like, I got to move. Kids are like, I got to get closer. So they understand no matter where they are they're in the splash zone. So it doesn't matter of direction. Here, there are only 2 directions. And that's it. All right, number 5, absolute value d plus 9 is greater than 3. So either this expression d plus 9 is greater than 3 or it's less than negative 3. Again, outside of 3 units of 0 in either direction. Less than is farther away, bigger negatives. We're going to subtract 9 from both sides on both sets of these. This is the solving of compound inequalities, where we get d is greater than negative 6 or d is less than negative 12. Those are the values of d that'll satisfy this set. You can tell that 0 would be a part of one of the sets that qualifies. Here's 0, here's negative 6, here's negative 12. D can either be here or here, and it should work out. Again, 0 included. Is 0 plus 9 absolute value that greater than 3? Yes, it is. That didn't double check everything, and I'm not intent on double checking most anything unless they force it on me or it really makes sense to talk about it. And that's not the case here. Absolute value of h minus 5 must be within 10 units. Not say h must be within 10 units, but h minus 5 must. So between this and this. So less than is within these 2 sets of units. I'll add 5 to both sides. Like that. It's kind of a weird way that I shuffled that around. H has to be less than or equal to 15, and h has to be greater than or equal to negative 5. Or h has to be between negative 5 and 15. My preferred go-to. Now you can see for these and cases, I am writing them split up like that. I don't need to do that. Maybe for some of maybe I can do what I do for the other sets and alternate. Like when I either choose to have negative variables on the left side versus positive variables on the right side, maybe I can alternate. So this time I did an and where it was like that. 0 is a part of it. Next time I'll write and as a single compound inequality thing like that to solve when I'm between two numbers. 0 would work. 0 minus 5 is negative 5. Absolute value of negative 5 is 5, which is less than or equal to 10 still. Number 7. Absolute value of 2s minus 7 is greater than or equal to negative 1. Now, given that that right side is negative and this absolute value is isolated, we just saw this on problem number 2. We saw this on the lecture portion. This is an all real numbers case, and we're going to graph it. This is an all real numbers case because no matter what I substitute for s, I will take the absolute, I'll multiply it by 2, I'll subtract 7, and I'll take the absolute value of it. No matter what that number was, the absolute value of any number can only be 0 or positive. Every solution will be always greater than negative 1. Every number 0 or positive is always greater than negative 1. So my solution just looks like everything. S is everything in the world. Number 8, a little, even though it's still infinite, a little less than all real numbers, a little more particular, a little more filtered. As we're greater than 7, we must be 7 units outside in either direction, greater than the 7 or less than the negative 7. Let's solve them. Subtract 5. And you notice on these, I'm kind of treating them all as the same thing. Like minus 5, figure what those ones are out right there. Because we're really just doing the same steps. So kind of comparing them as I go. Like when I divide by 4 on this one, I'm going to get a fraction. When I divide by 4 on this one, I'm going to get a nice old integer. So this is 1/2, 0.5. This one here is negative 3. This or that, not this and that, this is a split. Greater than 1/2, less than negative 3. This way for C, this way for C. 0 not included. Let's try that. 0 plus 5, 5. Absolute value of 5 greater than 7? I don't think so. 0 doesn't work. It shouldn't. That all worked out. Number 9, absolute value of 5p. 5p plus 2 is less than negative 4. We can't take the absolute value of something and get a negative out. So we can't ever be less than negative 4. This is a case where nothing can really be written. This was like number 2 as well. Wait, was this one like number 2? Anyway, this is a no solution case. There's nothing to kind of bring about, right? You can't be less than a negative. You can't be a negative in an absolute value case. Number 10 will be within 5 units. So this is one where, sure, we'll do the thing. It's just this is a negative inside of here, so I'm fretting it a little bit, but we did do this at the time for section 2.5. All right, we have to be between 5 units of 0 for either expression, either direction of this expression. So 9 minus 4, I must be between 5 units this way and this way of this expression. You can write it like that straight up if you want to. I generally don't, but you could. We're going to subtract 9 among all sides of this set. This is, again, what we did in section 2.5. That's a negative 4. This is still a negative 4n, and this is a negative 14. Now we'll divide everything by negative 4, and many things will happen here. First of all, even if you cancel those out, these don't cancel. That becomes 1, and it's a positive. This also positive. It's a fraction. Reduces to 7 over 2, which is also 3.5. And because we divided by negatives, inequalities will flip like this. Now, we don't ever write compound inequalities in this direction. Flip everything over. Everything over. So now the 1's on this side, the 7/2 is on this side, and the inequalities look this way. So this is our final set. 7/2 again is around 3.5, which is more than 1, which makes sense for this set. Here's 0. Here's 1. I'll put 3.5 here. 3.5, and this is what n is allowed to be. 0 does not belong. Let's see. Absolute value of 9 is less than 5. I don't think so. So that doesn't work. But that set should. Now, number 11 and onward seems to be problems where the absolute value quantity is not yet isolated. So we got to make that so. So we have 6t minus 7 wrapped in the absolute value. Here's a minus 8. So before we split our condition, we have to first add 8 to both sides of this, and then we'll get things sorted out. Absolute value of 6t minus 7 is greater than or equal to 11. So this is either greater than or equal to positive 11 or less than or equal to negative 11. Hopefully you're catching on how this split works, when it does, why we do what we do. This time we'll just treat one at a time, see if it feels the flow is any better. We'll divide both sides by 6. This is greater than or equal to 3. I actually like that flow pretty well. But we still have to go on this side. Here's a fraction. Divide by 6. Negative 4 over 6 reduces to negative 2/3. So our split of or is is outside of 3 in one direction, outside of 2/3 in the other direction. It includes both, closed circles and all. So we got our 0, negative 2/3, and 3 hanging out over here. T, 0 doesn't work. You can double check it. I'll be good. I'm leaving it. Number 12. We have problems to do, right? A lot of these are kind of 2 problems in one. Number 12, absolute value of 3j minus 1 plus 6 is greater than 0. When I subtract 6 from both sides, suddenly we are taking absolute value and it has to be greater than a negative. That will always be true. So once we hit here, we have an all real numbers case. I guess this can technically be graphed, so I will. We just graphed just a number line that's completely filled up. I'll include 0, of course, because all real numbers include 0. So we can go left to right of 0. We can be 0. J can be anything in the world. It'll always work. For absolute value cases, of course. Number 13. All right, so in this case here, we will divide both sides by 3 to begin with, get the absolute value portion by itself. Greater than 6. We have to be 6 units outside of 0 in either direction. So this is an OR case, greater than 6 or less than negative 6. This is one of those things where, because both of them have negative m's, I'll do one of them where I'll keep m negative on this side. So I'll do like, boom, like this. So negative m is greater than negative 12. No, negative 12. What is that? Negative 8. Negative 8. And then divide both sides by negative 1, which means the inequality is going to have to flip. That's m is less than positive 8. Now on this one, I'm going to go ahead and add the m to this side. Again, I'm just being diverse with these. It's up to what you want to do. Add m to one side, add 6 to the other side. This says m's here, 20's here. If you want to actually flip it over, this will say m is greater than 20. So it's an OR case, and it still seems to be an OR case. In order for this to be right, m must be less than 8 or greater than 20. Now, I never had to flip this inequality over. I flipped everything over, but I never flipped the individual, just one part over, because I never divided by a negative. But I turned the whole thing around, which flipped it over, and it still satisfies the set. So less than 8 or greater than 20, which is a split. Less than 8 includes 0, by the way. Anything between 8 and 20 won't work. But these will. And again, the OR case needs to be there for splits. Number 14. A couple things are happening on this one. So on 14, we do have something multiplied outside the absolute value, which we'll divide. And it's negative. So when we divide by the negative, not only will this be by itself, but the inequality will flip and the sign will change. Both of those are really crucial for this. Absolute value, something greater than or equal to a negative. It'll never be equal to the negative, but it will always be greater than the negative, no matter what you substitute here. Once again, we have all real numbers. I do like that they have the special cases embedded within this problem set. You know, that it's not just its own little block of problems where it's more likely to happen than not. I do like that they're all just within here, because you never know when to expect it. You just have to be on your toes and prepare it. I don't like if half the problems are like that, but get a good mix of them. At least it's less time to do those ones. Even less if we get a no solution case again. I'd be okay with one of those. Number 15. We have 2 things to do to isolate the absolute value. I'm going to first add 13 to both sides, like so. And now we have 2 times the quantity 3w plus 8. And that is 8. Now we'll divide both sides by 2. Everything seems to be positive, so at least we're going to have to, stick within the set. So absolute value of this is within 4 units. This is where I'm going to write and then I'll combine them at the end. So either 3w plus 8 is less than, not either, I can't say that. It must be less than or equal to 4, and, because either implies or, 3w plus 8 must be greater than or equal to negative 4 as well. Let's try a couple minus 8s. Couple divided by 3s. W must be less than or equal to negative 4/3. That's negative 1 1/3. So to the left of that number, as we subtract 8 here, it gets even smaller to negative 12. And then we'll divide by 3 here. That's greater than or equal to negative 4, which is smaller than negative 1 1/3. So as a single inequality, that's the lower bound. This is the upper bound. There is our full set that I want to write, like that. As a graph, again, they're both negative, so here's 0, not included. Negative 1 is about right there, and here's some negative 4 biz. Close circles in between, as compound inequalities with and cases will do with overlap. There we have it. Okay, a few more. A lot of work on these ones. Number 16. Whew. Okay. One step at a time. Subtract 5 from both sides to isolate the absolute value. Then divide by negative 3. Now what will that do? A few things for us. Get rid of that, isolate the absolute value, flip the inequality, and make this positive. And of course it divides it. So this is a standard case, not a special case. Either greater than 6 or less than negative 6. Like so. These are the cases where, again, I can do that kind of flip-floppy thingy. So I'm going to subtract 2 from here, keep this one positive, or keep this one negative, excuse me, keep this one on the left side. Divide by negative 4, which flips the inequality again. That's u is less than negative 1. This one here, I'm going to go ahead and add 4u to both sides, while I also add 6 to both sides. Let me move this over a little bit. Meanwhile, I will also add 6 to both sides. So make that positive. And again, if you're asking, wait, why'd you do this for this one and that for that one? I'm diversifying what to do. I'm giving you both instances of it. If 2, remember this is 2 is less than u, that's also saying u is greater than 2. And there's our or case. And there we have it. Less than negative 1 or greater than 2. So have you determined over this time whether you prefer to have the variable term positive on the right or negative on the left, understanding that you for yourself cannot forget to flip the inequality symbol, or in these cases, it's probably best in your best interest to flip the entire inequality. Ultimately, as for me, I'm probably better off with the negative on the left. In most cases, I prefer my things on the right, but in that one on the left, I don't mind. I don't know, actually. That's why I do both. And it's great to kill 2 birds with 1 stone in one individual problem and go like, well, you get to see both for yourself and make your decision. Case in point, we might have to do that here. Interesting. We subtract 7 from both sides and we get 0. Does that mean no solution? No, not necessarily. Greater than 0, and we divide by 6. 0 divided by 6 is still 0, right? 6 times something is 0. That thing must be 0. Negative f plus 3 is greater than 0. Now, we have seen equal sign versions where there's only one answer, but that's because it says equals. There's no such thing as positive or negative 0, which is the same thing here. However, to be positive here, that means that this can either be a positive number or this can be a negative number. Greater than positive 0, less than negative 0. Greater than 0 or less than 0 is our setup. So once again, would you rather? You know what? On these cases, I'd probably just rather add f. Even though we might have to flip the idea of the inequality as a whole, adding f here is just a one-step deal for now. I know we have to flip it over there. F can either be less than 3 or f can be greater than 3. That's a weird way of saying it. Here's another way we can say this. F can't equal 3. You know what inequality also kind of means? Unequal. This is a version of an inequality. It's a different kind of symbol, but f can't equal 3 is another way to say that. How do we say that f can be any number that's not 3? Think about how all real numbers looks, although this time I have a boundary value. All real numbers looks like it can be anything. F can be anything here, anything here. Oh, but guess what? It can't be 3. Boom. F can be anything but 3. This, that, 0, the other thing. 3 is the only thing. Interesting problem, kind of cool one. And that would be the graph. Number 18 says, yo, why do y'all got to be like this? I'm going to give you your fraction bits. Now, 2/3, I said bits, B-I-T-S. Now, 2/3 times 4v plus 6 minus 2 is less than or equal to 10. Now, it's possible to distribute 2/3 into here if you know what you're doing and why absolute values work that way. I'm going to refrain so that you don't assume you can do it in any such situation. So we're just going to keep it like so. As we add 2 to both sides, and now we have less than or equal to 12. Now I'm going to multiply both sides by 3/2 to get rid of that. In one step, multiply that. The numbers will change a little bit. And 12 divided by 2 is 6. 6 times 3 is 18. Okay, so we're at this stage here. We've seen it. We're going to be between 18 units of 0 for this expression. This time I'm going to be doing it like this. Between negative 18 and positive 18 in either direction. Let's go ahead and subtract 6 in all which directions. And let's divide by 4 in all directions like that. And we get -6, or v is between -6 and 3. I haven't been double checking these. 0 does satisfy the in-betweenness of that. We can go and take a look at it if you'd like to, and then we'll go ahead and move forward to the next set of problems. So here's v between and including those. Again, 0 should work. Let's try that. 4 times 0 is 0, plus 6 is 6. 2/3 of 6 is 4. Absolute value is 4. 4 minus 2 is 2. 2 is less than or equal to 10. 0 works. 0 works. Okay, good heaping of the problems. Not quite halfway done, though. So, number 19 and 20 on modeling with mathematics. Excuse me, I had some sniffles. The rules for an essay contest say the entries can have 500 words with an absolute deviation of at most 30 words. Write and solve an absolute value inequality that expresses the acceptable number of words. So if X is our amount of words, let's say W. If W is our amount of words that we can have, and we take the difference of our amount and 500, that must absolutely only be 30 words plus or minus that amount. That's where we say we must stay within 30 words of 500. The difference between our amount and 500 must be within 30. That's how that's set up. Now, there are other ways that you can probably make more sense of that you can still get the same kind of answer. To be between these, we have to be between negative 30 and positive 30 from there. So when I add 500, and remember, this is what I did with section, what was the section? I think it was 1.4, section 1.4. I said it's not so much 30 plus 500, negative 30 plus 500. This is 500 plus 30 and 500 minus 30, right? That's what we're doing. Our amount of words can be between 500 plus 30 words and 500 minus 30 words. So that's what I was saying. There's probably an easier way to get to that scenario for yourself. Do we have to graph it? No. We can be between 470 and 530 words. That deviation of 30 says plus or minus 30 words from 500. 470 to 530. But as an inequality, like that. Okay, number 20. The normal body temperature of a camel is 37 degrees Celsius. This temperature varies by up to 3 degrees Celsius throughout the day, plus or minus 3 degrees. Write and solve an absolute value inequality that represents the range of a normal body temperatures in degrees of a camel throughout the day. So again, if you imagine plus or minus 3 degrees from 37, I think we know the answer is going to be between 34 and 40. But let's still practice the inequality bit. A camel's temperature, I'll put T. Camel's temperature well, lowercase t is normally time. Let's do uppercase t for temperature. I could also do x. Subtract the 37. The difference between the camel's temperature and that 37 can only be within 3 degrees Celsius of the norm, at least for our setup. So same thing as before. This time we'll say the and scenario. Less than or equal to 3 and yet greater than or equal to negative 3. Again, the difference between the temperature and that standard one. Add 37. This is where it says less than or equal to 40 degrees Celsius. 37 minus 3 is 34 degrees Celsius. And as a whole, compound one in between, you got to be between 34 degrees Celsius and 40 degrees Celsius for the camel's temperature. We do not graph. Okay. Halfway through. Numbers 21 and 22 describe and correct the error in solving the absolute value inequality. Well, in number 21, they didn't consider the two different conditions. This may be one answer, but there's a lower end answer as well. To be within 20 units of 0 with x minus 5, we need to be between 20 units on the positive side and 20 units on the negative side. So they are missing their negative condition, greater than condition. They are missing their negative inequality condition, where they must be greater than the negative. This is also an and compound inequality. So we've had a few and sets recently. So this one, we have x, absolute value of x minus 5 is less than 20. So either, not either, but these two conditions must be met, the one that they wrote and this one here, or they can set it up as a compound to begin with, but greater than negative 20. So they did add 5 on this one to get 25. And they need to add 5 here to get greater than negative 15. If you're greater than negative 15, that includes 0, but all the way down to negative 15, you're good. At negative 15 or past it, no good. Do we graph? No, we do not. So here's one set. I can also write it like so, my preferred. Personal preferred. All right, number 22. X plus 4 is greater than 13. Everything is kind of backwards with this condition here because they called it an and then they treated it like an and. They basically treated this as if this said less than. They basically treated this as if this said less than here. So I'm just going to treat it like an or and split it the other way. They treated the problem like the inequality was a less than instead of a greater than. Because everything else is based on this. I'm guessing the rest of their answer stuff is fine for what they put. Given, like number-wise. But everything else kind of has to change. So absolute value of x plus 4 is greater than 13, where now it's supposed to be actually greater than 13 or less than negative 13. So when we subtract 4, we still get their negative 17 and their 9, but greater than the 9, less than the negative 17, and we can't write it as a single compound because it's not an and set. So it's not between negative 17 and 9, it's outside of negative 17 and 9 that this works. Okay, in exercises 23 to 26, write the sentence as an absolute value inequality, then solve the inequality. No graphs again, no graphs asked. So let's kind of move down there. Okay, number 23, a number is less than 6 units from 0. So less than 6 units in either direction. We can be less than 6 units to the left or to the right. So like that. So x can be between 6 and negative 6. And that would just be the answer. There's nothing else I got to do there. It's got to be less than 6 units from 0, which is greater than negative 6 in that case. That's why the graph would be the joining of. Number 24. A number is more than 9 units from 3. Okay, so more than 9 units from 3. Let's see how I want to say that. 9 units in either direction of 3. Now, if we saw previously, our difference between our numbers has to be more than 9. So more than 9. So the thing is, we'd have to say some x minus 3 inside of here, because 3 will be the middle value. I'll show you what I mean when we do an actual graph of this thing. But when we solve this thing, it's either x minus 3 is greater than 9, or x minus 3 is less than negative 9. So add 3, where this now says x is greater than 6, or x is, 12. X is greater than 12, or x is less than negative 6. I should probably rewrite that. X is greater than 12, or x is less than negative 6. Doesn't look much better. So here's 12. They didn't ask to graph, but I need to support this one so I can use it in the future. Maybe talk about this a little bit better. Here's 3. Here's 9 units from 3 this way and 9 units from 3 this way. Minus 9 plus 9. Remember, the minus 3 here says the difference between our number and 3. The difference between our number and 3 must exceed 9 units in either direction. To do that, we have to have 3 be in the middle of that. Because 12 minus 3, oh, we didn't fully graph this, but boom, boom. 12 minus 3 is 9. Negative 6 minus 3 is negative 9. That's 9 units in either direction. We have to be more than that. That's why that works out that way. All right, number 25. Half of a number is at most 5 units from 14. Half of a number is at most 5 units from 14. So just like, okay, let's first let it say a number. A number is 5 units from 14. How do you go 5 units from 14? You take the difference of that number and 14 and you get 5. If it's at most 5 units from 14, in either direction you'd have this. If you have half of a number, it would look like that. Sorry, at most. At most 5 units from 14 would look like that. So we have that setup. Half of a number is at most 5 units from 14. Boom. So now we're going to be within 5 units from 14 in either direction, 5 or negative 5 for this expression. I will add 14 to all sides. It's 9. And then I will multiply everything by 2. Okay. Half of 18, 9, is, when you subtract 14, it's 5 units away from it. It's there. 9 is 5 apart from 14 in the left direction. Half of 38 is 19. 19 is 5 away from 14 in the right direction. That's the most you can go. That's the most you can go. You can't go more than 18. You can't go 15 and 40 and things like that. Number 26. Twice a number is no less than 10 units from negative 1. 10 units from negative 1 in either direction is, we have to take the difference of your number and negative 1, which means you got to add 1. If you notice, this one said half a number. This one says twice a number. So twice a number, the difference between this number and negative 1 is 2x plus 1. So I'll put a plus 1. And we can be no less than 10 units away from it. That means we can be 10 units away from it. We can be more than 10 units away from it. So we can be like that. So we can be this or that. Greater than or equal to 10 or less than or equal to negative 10. 10 units in either direction. Either direction. Now, these will both be fractions. That means dividing by 2, I'm going to make them decimals. I can divide this by 2 and get 4.5. Or I can divide this by 2 and I'll get negative 5.5. If I double either number, twice this number is 9. 9 is no less than 1 unit away from 10. If I do anything bigger than, no less than 1 unit. No less than 1 unit from 10. Hold on. Is that how I want to say it? I think so. If I do something bigger than that, I get like 5. You double 5, I get 10. Is that no less than 1 unit from 10, or is that no more? Hold on. Did I say that right? Twice the number's no. Oh, 10 units from negative 1. Oh, got it. I was saying it the other way. Yes. Okay, that's good. We're good. I was like, did I do this backwards? It's not 1 unit from 10, it's 10 units from -1. Got it. All right, number 27. Problem solving. An auto parts manufacturer throws out gaskets with weights that are not within 0.06 pounds of the mean weight of the batch. I didn't understand a lot of that other than I saw mean, but I did say, oh, they throw out gaskets. I see. They toss them. They discard them. If they're not within 0.06 units of the mean weight in either direction, they're gone. Got it. The weights in pounds of the gaskets of a batch are 0.58, 0.63, 0.65, 0.53, and 0.61. Which gaskets should be thrown out? We have 5 values. We divide this by 5, and we get the mean value of it. And that will be done in the calculator. Give me a second. Of course, it's not working. Every time I start a new video and leave this calculator up, it seems to not work the next time. So apologies as this happens. Maybe you can beat me to the punch as I'm reloading up my calculator. Again, you can't see this. Here, I'll let you see my calculator. I just loaded it up again. Now you can't see it. All right. Hold on, I lost my screen. Okay, 0.58. Oh, you know what I want? Parentheses here. 0.58 plus 0.63 plus 0.65 plus 0.53 plus 0.61. Divide this by 5, and you get 0.6. Now, 0.6 being the mean value, I'm actually going to write 0.60. The reason for this is because our number we're talking about is 0.06. Now, as an inequality set, our difference needs to be 0.06 units away from this difference, either direction, like this. That means that our difference between our numbers and that needs to be between positive and negative 0.06, like that. When I add 0.6 in both directions, and again, I know it's probably easier, it is for me too, to just do, which we're about to do it, add 0.6 to this number, subtract 0.6 from this number. That's exactly what we were trying to do. We're still practicing why this thing's written in a finite, in a confirm, in a way that this is and how this kind of works. So it needs to be between 0.66. What are the units? What are we talking about? Pounds? 0.66 pounds is the upper limit. 0.54 pounds is the lower limit. All right, what doesn't belong in that set? We are good here, 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 and here. The only one that's not good is this guy right here. So 4 of them are accepted. 1 is thrown out. Which one do they want? Which gasket should be thrown out? The 0.53 pound gasket should be thrown out. It doesn't fit within that range. There is an absolute deviation. All right. Okay, number 28. Looks like another absolute deviation question. 6 students measure the acceleration in meters per square second of an object in free fall. The measured values are shown. The students want to state that the absolute deviation of each measured value x from the mean is at most d. Find that value of d. So, on number 28, we need to find the average of these numbers. We have to find out how far the farthest one is from there, and that will represent the d value. I need to think about whether we're just doing a test among all the numbers or how that will work. I think we just look at the smallest number, biggest number, and find out that answer. 10.91. Okay, we have 6 numbers here. We will be averaging them. Of course, I should have just written this divided by 6. Add these up. Divide by 6. I'm going to go ahead and do this in the calculator again. So, come along with me and see how it works. All right. It works again. Plus 9.52 plus. Now, these aren't arranged in order, which means we have to work harder. Whoops. To figure out which one's which. I hope I typed it right. Divided by 6. At least it's a clean number. I'll trust I did the right answer. So that's 10.05 as an average. Okay. So I'm thinking about how to make this. Listen, I know what I can do as far as find the smallest number, biggest number, things like that, but I want to do it as in if I set up an inequality to solve for D rather than did something else with that. So basically, like, we'd have to plug in that certain number for X, but our scenario is saying that we have to be within D units for that at most D. Something is at most D here, where we take this number minus 10.05. So as a whole, you know, X minus 10.05 needs to be between D units this way and negative D units that way, like that. If we add 10.05, the best way for me to write this here, and again, I'm probably doing over, it's probably a little overkill in what I'm representing here, but I want it to look like the other problems right now. X needs to be somewhere between 10.05 minus D and 10.05 plus D. And again, I put those ones first to show you really adding or subtracting D units away from that mean. Now, what's the highest and lowest values here? So far, the highest and lowest value is 10.56. Now, this one's lower. So lowest here, highest here. What goes lower? Let's scan it. Okay, 9.52 is the lowest. What's the highest? 10.91. So I need to see if D... Let's do this. I want these to be X. I want 9.52 to become X in this case. This is for the low. 9.52 must be greater than or equal to the distance here, like that. If I add D to both sides and subtract 9.52 from both sides, then I'll get, and again, probably overkill in the problem and how I'm doing it, but it must be the same number in both directions, I guess. When I subtract those, what is that? Maybe it's not the same. What is that? That is 0.53. Is that right? 0.53? So D must be greater than or equal to 0.53. Okay. I don't know if that's how you do that. Because the other one says 10.9. Hold on. Let me read the question again. The students want to state the absolute value deviation of each measured value from the mean is at most D. Okay, so that's not the most. That's not the most for D. I don't even know if I have to write this as an inequality anymore. I just got to compare it to this end. Now on the upper end, the 10.91, I got to say that 10.91 must be less than or equal to the 10.05 plus D. I think this is more of an equals thing, but we take the largest of the values from here. So if we subtract 10.05 from both sides, that'll be, see, I don't think it's a greater than or equal to or less than or equal to. I don't think I'm stating that part quite accurately, but the idea is what's the farthest value from here and subtract it from 10.05. I think that's really as much as I need to state. And I think this one's larger. This is 0.86 away. This says D is greater than or equal to 0.86. So I might have... I might have expressed it incorrectly, but my thought to this is 10.91 is the highest value of the set, 9.52 is the lowest value of the set, 10.91 has the greatest difference from our average to it, and they said all of these values from the mean is at most D units away from there. So my guess is we say 0.86. I say we say D is 0.86. That's the largest value. I don't know if what I wrote as inequalities are right. That's kind of a weird way that I'm going about it. Furthermore, they're written in the same direction there. But I'm just going to say 0.86. That's the one that's the farthest away from that set. So again, I don't know if what I did for inequalities was right. I feel kind of weird on that part. Sorry. But the logic to what I said made sense. We found the average and the number that's farthest from the average that still fits that, and that's going to fit. That's it. Okay, in exercises 29 and 30, write an absolute value inequality that represents the situation, then solve the inequality. The difference between the areas of the figures is less than 2. Okay, now, we solve it? Okay, so the thing is, for the area of the triangle is 1/2 base times height. Now, 1/2 of 4 is 2, and 2 times x plus 6 distribute is 2x plus 12. 2x plus 12 square units for the area of the triangle. The area of the rectangle is length times width times length, I guess the way I put it, which is 12 square units. Now they said the difference between the areas is less than 2. The thing is, it doesn't matter which way you do the area difference, whether it's this minus this or this minus that, because we can write them in an absolute value state. But if I do this one, I think it'll make more sense to see it this way, even though, again, absolute value, it shouldn't matter. This has to be less than 2, the difference in this area and that area. Anyway, 2x plus 12 minus 12 is 2x. Did they say solve? They said solve. Absolute value of 2x has to be less than 2. So 2x needs to be within 2 and negative 2 units here. If you divide all sides by 2, this is a negative 1 and this is a positive 1. In order for this to be what it is, x can only be as little as, see, what do they want? They said solve the inequality, but this number can be as little as 5 and as much as 7. It can't even be 5 or 7. Because once you're 5, 1/2 of 5 times 4 is 10. 10 is 2 away from 12. It needs to be less than 2 away is distance. And I think that's part of what I was expressing, right? 2x plus 12 isn't automatically bigger than 12 just because there's a 2x there. If x is negative, it's smaller. So absolute value needs to stay within 2 means if x is negative, this becomes a smaller area than that. And that's something to just keep in mind when we got the problem going. Number 30. The difference between the perimeters of the figures is less than or equal to 3. So let's write the two perimeters here. I'll call this object 1 and object 2 just to get them started. So the perimeter of object 1, it's actually probably harder to write. This is a rectangle, so there are 2 lengths of x plus 1 and 2 lengths of 3. 2 times that quantity is 2x plus 2, and then we add a 6, which is 2x plus 8. The other perimeter is, I can probably just fit it right here. It's 4 x's. It's a square, so it's 4x. I can totally fit that over there. The difference between these two perimeters, P1 minus P2 is an absolute value. This must be less than or equal to 3. So 2x plus 8 minus 4x must be less than or equal to 3. And I don't know if this one nips me in the butt or not to have this negative inside here. 2x minus 4x is negative 2x. Here's the thing, though. If I wrote it the other way, I'd have to write 4x minus this quantity like that. So some people might mess that one up as well. So we're good either way that we write it. We have to be within 3 units in either direction. So I'll write these separately this time. Negative 2x plus 8 must be less than or equal to 3, and it must be greater than or equal to negative 3. That being said, what I'll do on this one is I will add 2x to both sides on this one, and I'll subtract 3 from both sides on this one, like that. And I'll divide both sides by 2 and get some weirded numbers here where x is greater than or equal to 2.5. And let's do this one over here. I'll keep the negative 2x on this side as I subtract 8 over. And I'll get greater than or equal to negative 11. As we divide both sides by negative 2, this turns into a positive 5.5, but we also flip the inequality. So we have to be between 2.5 and 5.5 units for x. For the perimeters, these are kind of nice questions. For the perimeters to be within 3 units of each other. 3 units also counts, but between 3 units of each other in that way. We can try some numbers like plug in 3. If I substitute 3 into here, this perimeter, hold on, we have an expression for it. First perimeter would be 6 plus 8 is 14. This perimeter would be 12. That's within 3 units because those are 2 units of each other. Okay, we still have 10 questions to go. We have 31 to 34. Tell whether the statement is true or false, and if false, explain why. So, if true, we don't have to explain why. That's my kind of question. I hope all of them are true, huh? Just kidding. All right, number 31. How long have we gone? An hour 4? Okay, this will probably end up going longest of the set. Of all the things. I forget. Section 2.1 might have been an hour 20 or so. If A is a solution of absolute value of x plus 3 is less than or equal to 8, then A is also a solution of x plus 3 is greater than or equal to negative 8. This is true. They don't ask us to explain why, so I'm not really going to write anything. But remember, when you have this set, you say either the inside is less than or equal, not either. But this is less than or equal to 8 and greater than or equal to negative 8. That's another part of what we actually write. Excuse me. So yes, that's whatever we solve for one, we're extending to solve for the other. Number 32. Now, by the way, if I flip that, that's not necessarily the case. If something is greater than or equal to negative 8, that's not necessarily within 8 units of it. So if they flipped these two portions, that's not necessarily true. Number 32, if absolute value of A is a solution of this guy, then it's also a solution of this being greater than 8. Well, this one's false because now, remember what I stated for the last one where I said, yeah, it's going to be true because it's within here. This is either greater than 8 or less than negative 8. So this one's actually false because A could be part of the negative solution set. A could be in x plus 3 is less than negative 8 because it is an OR case. It is an OR case. So I guess I should have been careful in how I stated it the first time you set it part of the set. It's that it's between this and that for the other one on number 31. Number 33, if A is a solution of this, then A is also a solution of that. Greater than or equal to 8. Greater than or equal to negative 8. No, it would be less than or equal to negative 8 as part of the OR set. That one's false. Or, I mean, a lot of this is false as far as the premise goes. We would be x plus 3 is less than or equal to negative 8, but also it could also be a part of this one right here, but that's not guaranteeing it's greater than or equal to negative 8. So I don't know if I'm explaining that well, but there are kind of two things that are weird with that. Even if they stated this, it would be false. Then A is also a solution of this. Even if it stated this, it would still be false because it could be a part of this as well. But the fact that they had this in the wrong direction, there are a lot of things that were wrong with that. And hopefully it's just making sense on what I'm saying on that. Last one, number 34. If A is a solution of x plus 3 is less than or equal to negative 8, then A is also a solution of absolute value of x plus 3 is greater than or equal to 8. So this is the flipped version, not flipped version of the top one, but it's a flipped version where you're saying, if it's a solution of this case, that would be an OR, then it's also a solution of the case that has both split. That would be true. So in this case here, anything that's, because this is a part of the OR split, right? So anything that's a solution of this is a part of the bigger set of solutions here, which also has the greater than or equal to 8s. So that one should be true. I know I'm saying things out loud and they make sense to me, and I know from the outside looking in it might not make sense to you. And I totally understand that. Hopefully you can at least see these answers as they are. I believe that those are correct. See those answers as they are and kind of work off of what I stated to build your own case. Number 35, making an argument. One of your classmates claims the solution of n is greater than or equal to absolute value of n is greater than or equal to 0 is all real numbers. Is your classmate correct? Explain your reasoning. You're forgetting 0. My classmate is incorrect. My classmate is incorrect because they are disregarding the fact that n could also equal 0. If they said absolute value of n is greater than or equal to 0, that would satisfy the all real numbers case. They could also say n is greater than or greater than or equal to any negative number, and that would satisfy the all real numbers case. Okay, number 36. Thought-provoking. Draw and label a geometric figure so that the perimeter P of the figure is a solution of the inequality P minus 60 is less than or equal to 12. I just got to make sure I'm within 12 units of something. So let's solve that. That means I must be within 12 units of 60 in either direction. That means either 48 to 72, just so you know. So P minus 60, it's got to be between positive and negative 12 units of 60. Therefore, when we do 60 plus 12 and 60 minus 12, we see what I was just bringing up. It's got to be between 48 and 72 units. So that's our perimeter. It says draw and label a geometric figure, so that's between there. Okay, let's make a big old triangle. Big old triangle. Now it needs to satisfy the triangle needs, which is that a plus b is be greater than c. Let's see. If I do 10, 20, and 30, well, that would be 60 exactly. Let's do, oh, that wouldn't even work for a triangle. Let's do 12, 20, and 25. 12 plus 20 is greater than 25, so that satisfies the triangle part. Perimeter 12 plus 20 plus 25 is 45 is 57, and 57 is between 48 and 72, which is what was needed. Whoopsie, 57. That is a check. Okay, it was open-ended. That's what I came up with. All right, number 37. That was a 36, by the way. What is the solution of the inequality absolute value of ax plus b is less than c where c is less than 0? What is the solution of this where c is less than 0? Explain. Oh, for the first one, it says less than c, but it says c is less than 0. So here's the thing. If it's less than, it says c is less than 0, I want to like give a negative c there for a moment. Just say, okay, I'm making it negative. If you divide by -1 in this case, like that, then suddenly this becomes, oh, hold on. I guess you wouldn't want to do that. C is less than 0. Okay, where c is a negative number, you can't get something less than a negative number inside an absolute value. This is a no solution case. Let's see, I'll just put c is less than 0. This is a no solution case. Where it's greater than c, where c is less than 0. Greater than a negative number, that'll be an all real numbers case. Okay, that's all we have to put. I thought we had to do some more math and solving. Okay. Explain? No. You can't take every time you take the absolute value of a number, it'll be positive or 0 or positive, which is never less than a negative number, and always greater than a negative number. The never and the always satisfy. No solutions, all real numbers. Number 38. How do you see it? Write an absolute value inequality for each graph. I'm surprised we didn't do one of these earlier. Wait, did we do these for the Did we do these in this section, or were these in the previous section that we did compound inequalities? Oh, absolute value inequality. Okay, I was going to say. Okay, here's what you want to do. You want to find the middle, you want to find the middle value, and in all these problems, it's 2. 2 is the middle value between -1 and 5, right? The distance between 2 and 5 is 3. The distance between 2 and -1 is 3. So we're going to be 3 units either within or 3 units outside of 2 in each set of problems. And a lot of them are kind of like the same or whatever based off this. So like +3 and -3, that kind of thing. So all these are plus and -3 in either direction. That means 3 is what we have to be outside of or inside of here. So here's what I'm going to do. I'm actually going to copy and paste this diagram. I don't know why I didn't do it before. I'm going to copy and paste this diagram so I can write the answers next to each and every one of them. That's a big set. So for the first one, let's see how big I can make it and still fit stuff. For the first one, or for all of these, 3 is on that other side. I have to be 3 units either outside of or within my set. Now my difference is from 2. My difference is from 2. So for these ones, I'm trying to say absolute value of x minus 2. I have to be outside of 3 units from there and including those for this one. For this one, I have to be within 3 units and not including them. For this one, within 3 units and including them. And for this one, outside of 3 units, not including them. So those are the 4 sets that we're doing there. That's how I see it, right? 5 minus 2 is within 3 units. -1 minus 2 is within 3. Excuse me, it's within 3. 5 is within 3 units of 2, I should say. -1 is within 3 units of 2. How do you decide which inequality symbol to use for each inequality? It's based on the... I decided based on the open closed circle part. open closed circle aspects, as well as whether my values needed to be within or outside of 3 units. Now, whether it was equal to or not was going to be the open versus closed circle part. 2 more questions. Number 39, writing. Explain why the solution set of the inequality absolute value of x is less than 5 is the intersection of 2 sets, while the solution set of the inequality absolute value of x is greater than 5 is the union of 2 sets. Well, it's kind of the same thing that I answered at the very last part in here. When you're within the less than 5, absolute value of x less than 5 means you are within, once again, within 5 units of 0 in either direction. So you're both greater than -5 and less than +5, representing the intersection of those two. Now, the big word that I glossed over was and less than that. It's the intersection of those two. Now, x is greater than, absolute value of x is greater than 5 means you are, what the heck? Means you are outside of 5 units of 0 in either direction. So you're both greater, so you're either greater than 5 or less, or, gotta emphasize that, or less than -5, representing the union of those two. That's it. Number 40, solve the compound inequality below. Describe your steps. Aha. So this, you know, we had a case of, I think it was the previous section, but we had a case where it's the way that I invented it. It was 2 and sets together separated with an or. And now we have not 2 or separated by an and, but we have ands within ands and ors within ands. Interesting. So this is absolute value of x minus 3 is less than 4, and this is going to be fun. Absolute value of x plus 2 is greater than 8. So this is not only 2 problems within a problem, it might be 4 problems or 5 problems within a problem. So here, I'm going to write these ones in blue. This is x minus 3 needs to be within 4 units of 0 in either direction. Oops. Hold on. Boom. So it needs to be within here. Add 3 among all sides. So like that, we have to be between -7 and 1. Now, the and thing states that whatever was true there must be satisfied now always. I can never have any answers outside of -1 and 7, including those that will be part of the entire set, because there's an and here, and this needs to stay within those. Now, this one appears to be a split. I'll do this one in green. This x plus 2 must be greater than 8 or less than negative. I keep doing the equals on the other one. Or less than -8. Now I'll subtract 2 among all these sets. And here I'll get x is greater than 6 or x is less than -10. Now there's an and joining these things up as a whole. Keep in mind that as we see, let's see them as a whole graph set, but keep in mind, because this is an and, we need to treat the overlap of these two. Only overlap counts. So I'm just going to put 0 in the middle like that. Here's -10. That's not a 10. Hold on. Here's -10. Here's -1. Here's 6. Here's 7. Okay, all these numbers matter for us. The blue is important. We must be within this set here. Otherwise, it don't work. Now, for overlap, we have to be greater than 6 or less than -10. So here's the thing. Where does overlap count? Overlap is right here. Anything -10 is not part of our overlap. That means nothing for us. Oh, I'm sorry. This is not overlap either. No overlap, no overlap, no overlap. Here's 6, overlap with blue. Here's 7. Here's the overlap. This is the only place between 6 and 7 where there is overlap of these two. Not including 6 and 7. X is only between 6 and 7. I solved each inequality, and I sketched both them on a number line and found the overlap where they intersect, and that's it. Now, I'm not going to double check because that means I have to plug in numbers like 6.5 and whatever, but 0 will only work for this one, not for this one. Negative 12 will only work for this one, not for this one. Things like that. The only ones that work for both are between 6 and 7. 6 only works for this one, not for this one. 7 only works for this one, not for this one, stuff like that. And that is it. And guys, that is it. That'll do it for this one. This is Mr. Robinson. Thanks so much for watching. I think this broke that hour 20, so I think this is the longest one of the sections, but still probably shorter than anything from chapter 1 sections. Don't expect other chapters to have sections this short. We've lucked out in having inequalities spread out in such a way that I got to go pretty steadfast in certain ways, maybe a little too fast for others. We still got the chapter review to go and the chapter 2 test and cumulative assessment, which will include questions from chapter 1. But thank you guys so much for watching. Take care. I'll see you in the next one.